let us see slope stability analysis of an embankment dam. So this is just for steady seepage condition, which is downstream slope stability, we will see. So the question is, determine the factor of safety for the slip surface of the embankment dam shown below on its downstream portion under steady seepage condition. So when seepage is continuously flowing, which is a steady seepage condition, then what will be the stability analysis? So we will see factor of safety against collapsing. So use the following data. So you have data, average unit weight of soil under steady seepage, you have 20 kilonewton per meter cube, and unit cohesion or shearing resistance 24 kilonewton per meter square. Angle of internal friction of embankment material, which is phi 25 degree. So you have slice. So you have 9 slice for this specific problem. You have 9 slice 1, 2, 3, etc. So just whether it is above or below phreatic line, just you have average unit weight. Average unit weight is given. Total 20 kilonewton per meter cube. So detailed data is given in this table. So you have slice number 1 up to slice number 9. So what is alpha in degree measure? Alpha, which is for each slice, you have angle. Then what is arc length? Arc length, and also area of slice and pore water pressure that will be developed under this. So for each slice. So you can see before we go to the calculation step, let me show you. Just this is actually for upstream, and for downstream similarly you can draw like this, which is very important, I think. So each slice you can draw the free body diagram. So you have normal, which is resistance force, rather than collapsing. You have normal, which is resistance, and also cohesion or shearing resistance to this direction at the bottom of the slice, to this direction. But T, which is driving, T is W sine theta, which is just sliding parallel to the collapsing failure plane. So W, you have weight of each slice. So for all slice, you can draw the free body diagram. So this is for a single slice. So before you go to the calculation step, what are the preconditions for the property of embankment material? The first one is unit weight of embankment material, which is average unit weight given, no submerged, no saturated. So you will use that value. So step 1, since average unit weight of embankment material is given, just average, we don't need to convert it to other unit weight, saturated, submerged, and etc. Bulk unit weight, moist unit weight, etc. You don't need to convert because already given, submerged or saturated not given. So this is average unit weight, whether above phreatic line or below. For each slice, simply you will use this average unit weight. So let us go to the calculation. So simply you provide a table which is just showing each slice number up to 9. Then you have alpha in degree measure for each inclination. You have arc length, you have, and also area of slice. For each slice, you have total area above and below phreatic line. Just this is the phreatic line. Then below and above you have. So for this specific problem, you will use the total area because average unit weight is given already. So pore water pressure under each slice given. So the first step is you calculate weight. Weight means gamma times volume. You simply gamma, which is average unit weight 20 given, so you multiply by W, by area times length, which is 1 meter length, gamma times volume. So 1 meter, then gamma times area, you just drag this. Then resisting force, which is N. N means W cos theta, as shown in the free body diagram. For each slice, you have this one. N is just normal, which is the resistance against sliding. So just you have W cos theta. So theta is given here. So you simply multiply. So you get this result. Then you can drag like this. You drag it. then driving force, which is this one, T, which is parallel to the failure plane or parallel to the sliding line. So this is W sine theta, which is this value. Simply W already you calculated, then sine theta, then enter, then you drag the N minus U. So normal force minus port pressure. If you see the free body diagram, this is U. U is going to the upward direction. N is to the downward direction. So N minus U. You calculate in the table. You calculate in the table, then you get this value. So summation, you just provide sum of these lengths, each length you have, then you sum up all normal force, all driving force, and also N minus U. Then finally, you can find. So this is average unit weight already given. But if you have both saturated and submerged unit weight of embankment material without any phreatic line pattern, which is above or below, without that, if you have saturated and submerged, automatically you will take average, which is average saturated unit weight plus submerged unit weight divided by 2. So if you don't have a phreatic line pattern like this, without this phreatic line pattern above or below, we will see. So just you will use average unit weight, okay? Average unit weight of the embankment material. Otherwise, simply now you take the given value. So factor of safety is given by this equation. I think you know this equation. This is just for downstream steady seepage condition. You will use this equation. So summation of change in L, which is change in L is the length of arc. For each slice, you have change in L, change in L, change in L. So summation of all will give you arc length for this slip surface AB. So length of slip circle, which is 2 pi r sigma over 360. So sigma is the central angle of the slice. This is a slice. You can see from the very beginning, you have here, then this is a slice. So once you have slice, this is just AB. This is AB, A to B. Then slip circle, you have sigma is central angle of the slip surface. So you can get, if not given, you can get arc length total. So factor of safety is just resisting moment divided by driving moment, which is cohesion times length. So C is one resistance, which is it will just add resistance to sliding. So C times L plus tan phi summation of N minus U over sigma T. So once you substitute this one already from the table, already sum up, then you get this value. So this value is just less than 1.5. So the embankment dam is not safe. So the downstream slope is being collapsing during steady seepage condition. So when seepage is flowing continuously through the embankment material, so the dam structure may be failed. So this downstream slope will be failed. So if it is not stable or if it is not safe, how do you check? So how do you treat the embankment material? So remedial measures. These are the remedial measures. Some of the remedial measures to have a safe embankment dam. So change the type of embankment material initially. Once you select them, you can change to improve shearing resistance, which is C, and internal friction angle, which is phi, and make the downstream slope more gentle. Downstream slope you can make gentle. The slope you can make rather than 3 to 1, 4 to 1 you can make, but it may increase the volume of embankment fill. But you don't have option to make safe. You can increase downstream slope and improve moisture content, lift thickness, compaction, number of passes of roller, machine, etc. During compaction, you can improve moisture content again. Moisture content to get what? Just maximum dry density and then maximum compactive effort. So most of the time, dry density and maximum dry density and moisture content, if you just maintain, then you will have a good compactive effort, maybe 95% and above. So that is important. So as a remark, if you have upstream stability of upstream slope during sudden drawdown condition, you can just check using this factor of safety, using this equation, sigma c times b sec theta plus sigma n prime can phi. So this n prime shows submerged. So w prime times n means cos theta. So w prime cos theta. So w in place of w prime submerged unit weight you have times here, then summation of t. So you will use this equation for that purpose. Okay, so I think once you calculate this one, so you can see this is a free body diagram for upstream slope. For downstream slope, similarly, you can draw. So no problem. So as an exercise, please refer already. This is just already uploaded in Telegram or e-learning. Please just do this exercise. Cross-section of an embankment, homogeneous embankment dam. So coefficient of permeability or hydraulic conductivity is given. The sketch of flow net determines the total seepage, etc. for water pressure. Already we have done such example. And the second one is somewhat different. So you have just this pattern. So you have angle. For each angle, you just take data from this diagram. You have angle and shearing resistance and layer 1, layer 2. You have 2 layers. So with this layer, you have this cohesion, unit weight, and also friction angle, etc. for 2 layers. So depth is given. So according to Felino's method, I think you can get from the handout description. So please try this one. So already we have covered stability. Just the stability analysis can be grouped into 4 conditions. Stability analysis of downstream slope during CD seepage, already done in the previous example, which is downstream slope, and the stability of upstream slope during sudden drawdown. So this is just according to that formula. Please try. And stability of upstream and downstream slope during and immediately after construction. And the last one is stability of foundation against shear. So stability of embankment dam may be just under shear. So at the base contact, it may be failed by shear. But embankment dam may not be failed by overturning and also sliding like gravity. But you may have shear, just foundation shear only. Okay, so thank you. If you have any question, you are welcome. Please send you via Telegram or email, or I think you can upload it e-learning again. Okay, thank you. Okay, so this is all about today's tutorial. Hopefully you liked the video. If you have any comment or doubt regarding this topic, please let me know and write down in the comment section below. I will definitely reply on it. And thanks for watching.